Hey class, it's me again, Professor Rourke. Okay, so I wanted to make a video regarding 2.6 homework, and 2.6 can be a little bit of a doozy because they're talking about limits at infinity, right? It's also called horizontal asymptotes. So a lot of this section, you probably may or may not remember some of this from your previous pre-calc classes, where maybe you were asked to find the horizontal asymptotes of like a rational function, right? But it goes beyond that into some uncharted territory. Also similar to the checkpoint and the limit notation, even if you know the horizontal asymptote, there's a certain way we kind of have to show it using limits. So, and then sometimes you don't. So there's a lot going on here. Okay, so number one, it wants you to interpret the graph. Okay, so they're talking about the limit as x goes to positive infinity, which is really saying like as you look all the way to the right-hand side of the graph, versus limit as x approaches negative infinity. So you look all the way to the left-hand side of the graph, and then C and D are kind of like what we've done already. Because if you remember, we actually did refer to vertical asymptotes in the previous sections. So it's sort of just combining it all together that like the limit as x approaches 1, both sides are going to positive infinity, and as x approaches 3, they're both going to negative infinity, and then they want you to sort of combine that together to write the equation of the asymptote. Okay, so there is just something we want to kind of be familiar with, is that when we're talking about the limits at infinity, really that is the same thing as finding the horizontal asymptote, okay, if it does converge to a horizontal asymptote. And then vice versa, when they're talking about the limit at like x is a number, but it's like going the like it's approaching positive infinity in the y or negative infinity in the y, that would be like the equivalent of a vertical asymptote, right? So that's just sort of one thing that they sort of start out in this section, is kind of relating what we're doing here. Okay, so talking about the limits as x goes towards infinity. All right, so same vibes for number 2. 3, it's heavy on the graph. 4 talks about using the graph. And then finally, when we get to 5 is when we actually start evaluating. So a couple of quick notes. These rules that you have learned previously are still helpful in terms of finding these horizontal asymptotes. However, the notation's a little different. So something I noticed in the checkpoint is just, I think we need some help and guidance in what you need to like show to get full credit. So for instance, number 5, yes, you could put this in your graphing calculator, no problem, right? But, or you could even look at this and you might remember from pre-calc that all we do is focus on the highest degree, in which case it's 3x over 2x. And then that tells us, since the degrees are even, the asymptote's 3 over 2. However, if this was a test question or a checkpoint question, I would need to see more work than that. So this is how we're going to do that. Okay, so this is only at the limit as x goes to infinity. Only then, not confusing this with the limits at x approaches 2 or 3 or anything like that we saw earlier. No, this is at the limit as x goes to infinity. So that's the first thing that we have to really pay attention to, is, are they talking about limit as x goes to a number or at infinity? If it is approaching infinity, they walk through how to approach these by like dividing everything by x. There's a lot of work. You don't have to show all of that. What you do have to show is that the limit as x approaches infinity of 3x minus 8 divided by 2x plus 3 is going to be the equivalent of the limit as x approaches infinity of just 3x over 2x. Okay, so you can do the same thing that we did in pre-calc, essentially, but it's going to look a little different. Okay, again, it's only because it's at infinity. And if you need any help, again, please definitely keep an eye on the textbook of like how this works, because they do go through like the long and painful way of how we can get here. But this is what you're going to want to essentially do. Okay, and then you can simplify 3x over 2x, which is just going to be 3 over 2. And then you're like, oh, actually, lo and behold, I'm just left with 3 over 2. Okay, versus number 6, same idea. Okay. And again, thinking back to pre-calc, you might see like, oh, this is bottom heavy because it's x minus 9 divided by x squared plus 6. But what we're going to rewrite this as is the limit as x approaches infinity of x divided by x squared. And then we simplify that. X divided by x squared is just 1 over x. And then this is what they refer to as in the textbook, theorem 5, which I feel like, I don't know, I just feel like that this makes sense in my head to say it that way. So whenever we have any sort of rational expression, a number over x or x squared or x to the third, anything x to the n, theorem 5 says it's just going to go to 0. Okay, now again, thinking back to pre-calc, we sort of hopefully knew that it's the degrees bottom heavy, the horizontal asymptote 0, but this is the work that we need to use to find it. Okay, so I hope that makes sense. I'm gonna focus now on number 8. Number 8 is an example of one of the graphs that two of the graphs they really like to use. Okay, so there's two main ideas that we need to really kind of get comfortable with in this section because they just love to talk about them. Okay, one of them is y equals e to the x. Okay, so the graph of y equals e to the x, whew, that doesn't look great, but just bear with me, is the graph where it has a horizontal asymptote as x approaches negative infinity, right? Over to the left-hand side, this graph is going to 0. But as we look to the right-hand side, it's going up to like infinity, right? It's increasing without bound. Okay, so they love that because they just use this all different variations of the limit as e to the x. So this is one of the examples of a graph that's like this is not fit the typical rational function form that we saw for the first ones there. Okay, the other one that they love to talk about is arctan because, and again, I know some people are like, oh, good, but even if you don't love trig, and it's a challenge for you, this arctan graph is one that you need to get down, okay? Because as we approach x goes to positive infinity, okay? So as we look all the way to the right of this arctan graph, it's going to pi over 2, okay? And as we look all the way to the left of this arctan graph, it's going to negative pi over 2, okay? And they love to use this. Okay, so let me go ahead and now revisit back to the problem because this actually combines both of them together, which is lovely. Whenever we have a composition of functions in this section, in particular, what I like to do is to sort of bring in a u. Okay, and at first it seems crazy if you haven't taken a calc class before. You're like, what, why? But later on in this class, and in Calc 2, there's going to be a lot more of this U vibe. So we might as well just try to embrace it now. Okay, so hopefully this makes sense. This is the composition of function. This is arctan of e to the x. So we have a function within a function, right? We have essentially arctan is f of x and g of x is e to the x, right? So this is what we do. We go ahead, and this just makes it a little simpler. Okay, and again, this is the sort of work that I would recommend you kind of get used to showing when you do your homework, because I know, again, when it comes to checkpoint and tests, it can be sort of a eye-opener. So what we're going to go ahead and say is that like u equals e to the x. Okay, and what we're going to do is we're going to rewrite this original limit in terms of what u is going towards. Okay, so we're going to come back and fill in what u is approaching after I have done some side work. Okay, so we say u equals e to the x. And so now I'm going to say the limit as x approaches infinity of e to the x is what I'm trying to figure out. All right, so then we go and we think about our lovely little e to the x graph that I talked about. And you're like, okay, as x goes to infinity of e to the x, this is just going to infinity. Right? Okay. Hopefully that makes sense. It could have been 0, but it's not. It's infinity because that's where x is going to infinity. If it was negative infinity, it'd be 0. Right? Okay. So now we can come back here and say, like, oh, okay. So as x goes to infinity, u is going to infinity. And now we can really just evaluate the limit as u approaches infinity of the arctan of u. And that's when we go back to our other graph that I talked about, where the limit of arctan as x goes to infinity is just pi over 2. Okay, so I hope that made sense. Again, that's just sort of like a general, super quick rundown on all of these problems in 2.6, but I know, again, there are a lot. I'm gonna make another video talking about how we're gonna approach number 10 using the squeeze theorem. That's gonna be where that comes into play. Okay, thank you, class. Keep me posted. I look forward to talking to you soon. Okay, thanks.